So next we're going to look at the instantaneous rate of change. So let's go back over what a secant line is. So a secant line is a straight line joining 2 points of a function. So over here we have a secant line that hits 2 points on this function. Remember, it's also equivalent to the average rate of change, or simply the slope between the 2 points. So again, the average rate of change, the slope of the secant line, is equal to delta y over delta x. A tangent line is a straight line that touches the function only at 1 point. So looking at the graph, we see that this straight line hits the graph at 1 point. The tangent line also represents the instantaneous rate of change, so the rate of change at 1 point in time. Since our slope formula requires 2 points, we cannot find the instantaneous rate of change or the slope of the tangent line using that formula. How can we use the average rate of change or slope of a secant to approximate the instantaneous rate of change or slope of a tangent? If we go back to our diagram, so if I took a point really close to the tangent line on the curve, I should get a good approximation for the slope of this tangent line or the instantaneous rate of change. That's the method we're going to use. We're going to take x values really close to the x value of the tangent line and approximate what's called the instantaneous rate of change. So example 1. The path of a football can be modeled by h of t equals negative 5t squared plus 30t plus 1, where h is the height in meters and t is time in seconds. So determine the instantaneous rate of change at 1 second. So what we're looking for is the slope of the tangent line. So the slope of this line that touches the curve at that 1 point, or what we call the instantaneous rate of change. Since our slope formula requires 2 points, we're going to start by taking points close to 1 from the left side. So we could start like at 0.5, then try 0.75, then maybe 0.8, 0.9, and keep on getting points closer and closer to give us an approximate of what the slope would be. So let's look at values close to 1 from the left. So as we're coming from the left side of 1. So let's start right away at 0.9. And our interval will be from 0.9 to 1. So we're going to find the average rate of change between 0.9 and 1, then 0.99 and 1, and 0.999 and 1. And hopefully we see as we get closer to the value of 1 that the rate of change will approach a number. So first of all, we need to find our delta t's. So this is 1 minus 0.9, so that's 0.1. 1 minus 0.99 is 0.01, and 1 minus 0.999 is 0.001. So we can see our delta t's, the distance between the 2 points, is getting closer and closer to 0. So our delta t's are going to 0. Now let's look at our delta h's, the change in height. So using your calculator, you're going to solve for h of 1 minus h of 0.9, and I end up with 2.05. So next one is h of 1 minus h of 0.99, and if you try that, I get 0.2005, and for the last one, I get 0.020005. Next is the rate of change. It's the delta h over the delta t, or the delta y over the delta x. So I'm going to take my delta h, 2.05, and divide it by 0.1, and you see I get about 20.05. Dividing the delta h over delta t for the next interval, I end up with 20.005, and for the third interval, 20.0005. So hopefully you see that the average rate of change, the delta h over the delta t's, are starting to approach the number 20. And that is what we call our instantaneous rate of change. but we've only approached from the left side. And in many cases, you should always check both sides. So let's check the other side. So this time we're now going to approach from the right side. So that means we would take values greater than 1 and try to get closer to 1 from the right. So approaching 1 from the right side. So let's say our first interval goes from 1 to 1.1. And we'll check our next one from 1 to 1.01, and then from 1 to 1.001. So we're going to look for the average rate of change, or the slope of the secants, and see if they approach a specific number. So our delta t is 0.1 again, 0.01, and 0.001. If we subtract the t2 minus the t1. Next, using your calculators, we're going to find h of 1.1 and minus h of 1. And if you do that, you get 1.95. For the next one, I got 0.1995. And for the last one, I got 0.019995. The average rate of change would be the delta h over the delta t, which gives me 19.5. The next one gives me 19.95, and the final one gives me 19.995. So once again, we see as my delta t's, as those t's get closer to 0, my delta h over delta t is again approaching 20. So we have verified from both sides that the slope of this tangent appears to be 20, or the instantaneous rate of change in height at 1 second is 20 meters per second. So let's quickly go over what we just did. So again, we were looking for the slope of the tangent at t equals 1, so the slope of this red line. And what we did is we took points close from the left and found the slopes of the secants connecting the blue point with the red point. Similarly, we took points from the right, so finding the slope of the secants connecting the blue points and the red points. And we saw that the secants, no matter which way we went, so from the left, they approached 20, and from the right, they approached 20. So we made the conclusion that the instantaneous, or the slope of that tangent line, is equal to 20. So we're going to do this one more time. So let's find the instantaneous rate of change at 3 seconds. So starting from the left side, we'll start with 2.9, just a tenth below 3. And then we'll go to 2.99 and 2.999. Now these are the three I recommend you try, always a tenth, a hundredth, and a thousandths below. Alright, so delta t, that's 0.1, 3 minus 2.9. 3 minus 2.99 is 0.01 and 0.001. Again, notice my delta t is always going to be approaching 0. Next is your delta h. So remember, we're going to have h of 3 minus h of 2.9. And when I did this, I ended up with negative 0.05. And then if I divide 0.05 over 0.1, I end up with negative 0.5. For the next delta h, I ended up with negative 0.0005. And when I divided the delta h over the delta t, I ended up with negative 0.05. Next one, I got negative 0.00005. 1, 2, 3, 4, 5, yep. And my delta h over delta t was negative 0.005. And we could try a few more, but hopefully you see that your delta h over your delta t is starting to approach 0. We're getting more and more zeros in front of that 5. So you can complete the next table, and hopefully you end up with delta h over delta t again approaching 0, which tells us that the instantaneous rate of change in height at time equals 3 seconds is 0 meters per second. Well, what does this mean? That means at that instant in time, the object is traveling at 0 meters per second. So what did we just discover? So here is that parabola. And you found out at 3 seconds, the slope of the tangent line is equal to 0. On a graph, the instantaneous rate of change or slope will equal 0 at our turning points. So you found at what time the ball will reach its maximum height, and at that point in time, the instantaneous rate of change, or the speed of the ball, will be 0 meters per second. Now from this point forward, it does not matter which side of the point you use to find the instantaneous rate of change for many of the functions we use in this course. So I don't expect that you check both sides. If you check one side from now on, we'll be good with that. Unless I ask you to check both sides, so approach t from the left and t from the right. So here are the questions that you should try, and good luck.